the last class, we basically finished up all of the review. There was a little bit more, but I think I'm going to skip it. If there's time today, maybe I'll get back to it. But let's go on to something that's really important, which is so 2.1, the concept of the limit. Concept of the limit. Okay, I haven't thought about this. Okay. So this is actually the most important idea. The most important idea in calculus. You could call it maybe the idea of calculus. I think it was basically introduced by Newton, and then it was made rigorous by a mathematician called Weierstrass in the 19th century. So 19th century. And we should say that it was actually foreshadowed by something called the method of exhaustion. Method of exhaustion of Archimedes. Okay. So there's an interesting story behind the method of exhaustion. It was not known for a long time how Archimedes, exactly how Archimedes achieved some results. Archimedes has some results which you think, oh, he could only do that. These are basically sort of calculus results. In the early 20th century, they found a palimpsest, which is a sort of a medieval reusable scroll. Like it's a scroll that that people would write on, and then sort of erase somehow, and then write on it again, and then erase it, and write on it again. And using imaging techniques, they were able to see what was underneath the top layer of the palimpsest, and underneath it was a document of Archimedes, in which he explained this thing called the method of exhaustion. And it's like, oh, okay, Archimedes actually had something that was very close to calculus, or that foreshadowed calculus. Okay, let's see. So, most important idea in calculus. If you understand this idea, then everything else will be a lot easier. Okay, so try for the next couple of days. Think very hard. Okay, because if you get this, then everything will be a lot easier. Okay. And I should say that in some sense it's a simple idea, but it's not a trivial idea. So it's a simple but deep idea. Okay. So section 2.1 is not exactly, it's not exactly the limit. We're not really going to talk about the limit itself, but we're going to talk sort of about the idea. Okay, so this is more like an intuitive section. It'll give you some sense of what the limit is, and then in the next section we're going to really tell you what the limit actually is. Okay, but for right now it's just sort of a touchy-feely idea. You'll have some sense of what the limit is. Okay, so maybe some of you have seen this sort of thing before. So let me ask, what does the limit of f of x as x approaches c being L mean? So in English, this says the limit of f of x as x approaches c is L. The limit of f of x as x arrow c, as x approaches c, is L. Okay. Yeah, Julia.
So like when your x value is approaching the c, whatever that is,
Yeah.
You're like approaching, your y value is approaching L.
Okay. Okay. So in terms of a graph, right? There's some point c. Right. Here's your x-axis. Right. There's some point c there, and as you take x's, as you take different x's, as you take different inputs and they get closer and closer to c, your outputs, let's say L is up here, right? Your outputs get closer and closer to L. Is that how most people have seen it? Those of you who've seen it, that's how you think about it, right? Right, the picture is sort of like you have something like this, right? As you evaluate, as you take values closer and closer, right? The heights get closer and closer to this thing L, right? So that's usually how it's described, like as x gets closer and closer to c, f of x gets closer and closer to L. What about at C itself? What about at C itself? Does this say anything about what happens at C itself? No, right? So it doesn't say, implies nothing about f of x at x equals c itself. Right? It could be L, or it could be somewhere far away, right? It may well be that the value is L, or it could be that the value is somewhere up, somewhere else. Okay. Just to amuse you, there. I don't remember if I saw this or if somebody told me about this, but at the University of Chicago, there's supposedly some bathroom graffiti, and it goes like this: the limit of fun x as x approaches the University of Chicago is 0. Okay, right. The informal motto of the University of Chicago is "Where fun comes to die."
Yes.
Okay. So yeah, there was when I was a graduate student at the University of Chicago. There was a poll or some sort of ranking of like the most fun universities. And so they gave 300 universities. I forget which was the top one. Maybe Florida State University or something was the top. And the 300th one was University of Chicago. The very last one was University of Chicago. And everybody was quite proud of that. Yeah. The students at that time all walked around looking like this. That's sort of how most of the undergraduates look at that time, and the graduate students look worse than that. Anyway, but I should say this humorous example has a purpose, which is that this actually says nothing about fun at the University of Chicago, right? The limit of fun as x approaches the University of Chicago is 0. That means that as you get closer and closer to the University of Chicago, right, so here's the University of Chicago, as you get closer and closer to it, fun goes to 0, right? Fun goes to 0. The limit is 0. But the limit at the University of Chicago could, fun at the University of Chicago could be actually quite high, right? So this example, this graffiti actually shows some level of ignorance, right? So yeah, so the limit being 0 doesn't say anything about the value at the intersection. Okay. 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 Yeah. If you look at the videos, I don't know how many times I've said this joke. So, so if you look at the class from the previous year, I've said the same thing in the previous year. So I always feel like, I'm gonna use the same joke. I'll try to find some new jokes. There's actually like mathematical joke sites, and I looked at them, but I haven't really read it. Okay, so the authors give a great set of examples. So there's a bunch of examples that they give. I'm going to use some of them because I think they're good. They illustrate some. They each illustrate a different point or facet of the notion of limit. Okay, and so here's what we're going to do. We have a bunch of functions. The first one is t squared. The second one is t squared, but only for t not equal to 0. The third one is t squared when t is not equal to 0, and it's 1 when t equals 0. Okay. And we want to think about what's the limit of each of these functions as t goes to 0. Okay, so just think about it for 1 minute. So just think about it for 1 minute and tell me what you think what the limits are. Okay, turn to somebody else and say what you think.
Yeah.
Okay, would somebody like to say what they think and why they think it? Kayla?
For the limit of t, which is 0, f of t is 0.
Okay, why?
By substitution.
By substitution. So you're saying, well, I'm just gonna plug in values, and as I see that I have this feeling that as the t's get closer to 0, the t squares also get closer to 0. So you're sort of imagining what t squared behaves like, right? Or maybe you're thinking graphically. You could be doing this two ways, sort of like, oh, as I put in smaller numbers, this thing also gets smaller, right? Or you could think graphically, right? Like if I'm looking at the unit parabola, then as t gets smaller, if t gets closer to 0, then the values get closer to 0. Okay, and then for the second one, Jennifer?
The limit is 0 again.
Limit 0 again. Why? Well, because you don't really care what happens at t equals 0. Right? The fact that this function's not defined, so this function's not defined at 0, but it doesn't matter. It doesn't matter. Right? For the third one, limit equals 0 again. Again, the same reason, right? For this third function, it is defined at 0, right? It is defined at 0. It has a value 1, right? But again, that doesn't matter. As you get closer, the values get closer to 0. Okay. So let me show you a slightly different way of thinking, which is sort of algebraically. So algebraically, you say, well, look, consider the absolute value of t squared. Let's consider the absolute value of t squared. That's the same thing as the absolute value of t quantity squared. Right? The absolute value of t squared and the absolute value of t squared are the same thing. Okay. And you think, well, for t of absolute value less than 1, the absolute value of t squared is actually smaller than the absolute value of t. Right, so if I'm looking between -1 and 1, if I'm looking at t between -1 and 1, and I look at if I look at the absolute value of t squared, well, that's going to be smaller than the absolute value of t, right? Is that clear? Anyone confused by that? Even if you're not confused, I'm going to explain it. The absolute value of t squared is the same thing as the absolute value of t times the absolute value of t, right? And if the absolute value of t is less than 1, then this is going to be, right? You're multiplying this thing by something less than 1, and so it gets smaller, right? So it gets smaller than this, right? If I started off with a number and I multiplied it by something, if I started off with a positive number and then multiplied it by something less than 1, it's going to become smaller, right? Okay. So absolute value of t squared is less than the absolute value of t, right? So as t goes to 0, the absolute value of t also goes to 0. Just to give some, right? As t goes to 0, well, the absolute value of t is going to be smaller than, the absolute value of t squared is smaller than that, right? As this goes to 0, that's also going to go to 0, right? That's also going to go to 0. And so this gives a way of algebraically explaining your intuition, right? You have this intuition already, like, oh yeah, if I take a small number and I square it, it gets smaller, right? This is how you could think about it, right? There's another way of making it more clear. Okay. Any questions about the explanation, the reasoning? Okay, second example. The limit as x goes to 5 of x squared minus 6x plus 6 over x. Okay. Take half a minute and then tell me what you think this is. Okay, turn to somebody nearby and say it is whatever it is. Okay, somebody like to talk? Marcella, how about you? I haven't called on you.
I got 1/5.
1/5. Okay, so Marcella says 1/5. And why do you think so?
Because I plugged 5 into the equation.
Okay, so you plugged in 5. So here's plugged in 5. Right? And you got 25 minus 30 plus 6 over 5. Right? So that's 1 over 5. Right? Okay, and that actually turns out to be true. Does that bother anybody? Yeah.
Just that won't always, like plugging in the value won't always work.
That's right. That's not always going to work. Sometimes it works. Okay, so your question should be, when does it work? Right? Right. We just said that you can't just plug in the value to figure out the limit. Right? That the value of the function at that point might not be at all the limit of the function at the point. Right? The limit could be some value, and the value, might be something else. Right? The value of f at c might be different from L. Okay. But sometimes it happens, right, for some functions, right? So for some functions, the limit of f of x as x approaches c actually is f of c. Okay. What kind? Okay. Right. And another thing that you're using is basically that the limit of a quotient is the same thing as the quotient of the limits, maybe, right? That you're taking, or maybe that you notice as x approaches 5, right? You notice that the limit of this quotient of functions is actually the same thing as the quotient of the limit of functions, right? Is that true? Is that always true? Is that always true? And so we'll answer both of these questions later. One more example.
I'm sorry, did you answer what kind of function?
I didn't. I said we'll answer these questions later.
Okay. Sounds good.
Yeah, this is sort of unusually sort of like a teaser.
Yeah. I feel pretty teased.
Okay. It's a, what do you call it? A trailer. Whatever. Yeah, for the next few sections. Okay. Another example. Limit of x squared minus 4 over x plus 2 as x approaches negative 2. Oops. X approaches negative 2. Okay. Again, take a minute and tell me what you think about it.
Is that negative?
Negative 2 on the bottom here. Okay, turn to somebody nearby and say, I think it is. Okay, would somebody like to say? Cole.
Is it 0?
Is it 0? Why do you think it's 0?
That's probably -2.
You plugged in -2. Okay, so you said, okay, let's put in -2. We're going to get -2 squared minus 4 over -2 plus 2. Right? You get 0 over 0. Right? You get 0 over 0. So is that 0? First off, is 0 over 0 the same thing as 0?
No.
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 Right, right. So if the denominator were something that's non-zero, then that would be 0. But you've got 0 over 0. Actually, that doesn't make this. It's almost you don't know anything at this point. Yeah. Julia.
-4.
-4. Okay. And why?
I factored out x squared minus 4.
Is
So
it?
x
Let's
plus
factor.
2.
Let's factor the top. Yeah.
So now I simplify to x minus 2 and I plug the x in.
Okay. Okay. So what you're using is the following fact that x is approaching -2, but x is not -2. Okay. So x is not -2 in this setting, right? So notice x is not equal to -2, right? And so these numbers are not zeros, right? Since these numbers are not zeros, you can cancel them off. Okay, so that's really what when you say, oh, I cancel them off, it's because they're not zeros that you can cancel them off. So here's really what's happening. X is not equal to -2, so x plus 2 is not equal to 0. X plus 2 is not equal to 0, so we can cancel. So we can cancel, right? And so we get the limit as x approaches -2 of this thing is just the limit of x minus 2 as it approaches -2. Well, that's going to be -4. So, but just to make it clear what we're using here. Okay, yeah, Becca.
Can we also plot, or not plot, but find 0, -1, -2, -3, -4, and then see if there's a pattern? So,
Do you mean you plug in different numbers for x? What numbers are you plugging in for x?
I plugged in 0, -1, -2, -3, -4.
Okay, and so you said, oh, I see. So you said, well, you plug it in points, and at 0 you got -2, at -1 you got -3, right? Right. So at 1 you got here you got -2, here you got -3, and right. So you're plugging in points. You think, well, this sort of looks like the line y equals x minus 2, right? So I mean that will give you, that could give you some hint about it. Yeah. So certainly, but to be more careful, you'd have to plug in points closer and closer to -2, right? Because plugging in points far away, you don't know what's going to happen close by. Okay. But in fact, it turns out that would work if you kept on plugging in points closer and closer, your values would get closer to -4. Okay. But there's a warning, which is that no matter where you stop, something could happen after that, right? So suppose I plug in a lot of points, but so here is -2, and suppose I plug in a bunch of points, and it looks like I'm heading towards -4, right? Looks like I'm heading towards -4, but after that point, something crazy happens. Okay, so plugging in values might give you some sense of it, but it's sort of, you can't trust it. You can't trust it completely. Better to use some actual reasoning, right? And you say, well, look, this function is the same thing as x minus 2, right? The point is that, right, the point is that this function is the same thing as x minus 2 away from -2, right? And yeah. Are there questions? Okay, now comes the most important part. Most important example. Okay, so So here's the idea of the example. These are examples 5 and 6 in the text. The idea is this. If the limit, and this is the key idea, this is the key. If the limit is actually L, we should be able to answer the question how close, so if the limit as x approaches c is L, we should be able to answer the question, how close to c must x be to ensure f of x is within 0.1 of L.
What does it say again?
Within 0.1 of L.
Oh.
Okay, so here's the picture. Here's the picture, right? Here is C, here is L, right? And we're saying that the limit of this function is actually L. If that's true, if that's really true, and somebody says, how close do you have to get to x? How close does x have to be to c to ensure that you're within 0.1 of L, right? So here's L plus 0.1, L minus 0.1, right? Okay. You should be able to answer that. And you would be able to answer that, right? You'd say, well, look, as long as I stay between here and here, everybody is within 0.1 of L. Right? Okay. So you'd be able to answer this question. Okay. Let me give a concrete example. So here's a simple example. Simple example. The limit of 2x as x approaches 3 is 6. Right? The limit of 2x as x approaches 3 is 6. Okay. 1, 2, 3, 1, 2, 3, 4, 5, 6. Right? Now, if I ask you, how close must x be to 3 to ensure 2x is within, say, 1 of L? What's the answer? If I ask you this question, here's your function, 2x, right? F of x is 2x. Here's the 3. Here is 6, right? How close must x be to 3 to ensure that 2x stays within 1 of 6? Within 1 of 6. Or actually, let me make it easier. First question, how close must x be to 3 to ensure that 2x is within 2 of 6, right? Between 4 and 8. Don't blurt it out. But yes, that's right. The answer is 1, right? X must be within 1 of 3 to ensure 2x is within 2 of 6. Right? Very good. Okay. Now I'm going to ask you another question. How close must x be to 3 to ensure that 2x is within 1 of 6? Think for 5 seconds. Or maybe 10 seconds. Okay. Sarah?
Yeah.
Oh, God.
0.5.
0.5, right? 0.5, right? If I want if I want everybody to stay between, so here's my 6 again. I want everybody to stay within 1 unit of 6. Well, as long as I stay within as long as my x's stay within 2.5 and 3.5, then I'm good, right? So as long as the distance of x from 3 is smaller than 0.5, we see that the distance of 2x from 6 is less than 1. Right? As long as the distance of x from 3 is less than 0.5, we see the distance of 2x from 6 is less than 1. Okay? Everyone all right? This is important, so if you're confused, ask now. Anyone confused? Okay. What if I say, how close must x be to 3 to ensure that you're within 0.1 of 6? Okay. So now I'm going to change this to 0.1, right? To make this thing less than 0.1, how close, how small must x minus 3 be? Again, think for 30 seconds. Okay, turn to somebody nearby and say what you're thinking. Okay, a lot of people are saying it. What's the answer? 0.05, right? 0.05 will do, right? As long as the distance from x3 is less than 0.05, you see that 2x minus 6 is going to be less than 0.1. You sort of see that from the picture. Okay, so what's the point? What if I choose some other number? Are you going to be able to find a place where where your values stay that close? Suppose I choose 0.00000001. Will you be able to find will you be able to answer the question? Sure, it doesn't matter. No matter what number I choose, you're going to be able to answer the question. Okay, so for example, if I say epsilon, my number is epsilon. Okay, my number is epsilon. How close? Right, you should be able to answer the question for the limit to BL, should be able to answer the question, how close must x be to C to ensure f of x is within something of L. Okay, and now I'm saying that you should be able to do it for. So, what if I say epsilon? What are you gonna? What would be your answer? 1 point on the exam for whoever gets this first. Well, okay. What am I gonna do? Okay, I'm just gonna. No. What am I gonna do? There's too many people.
Points to the brave.
They're all brave. Bias, what is it?
Epsilon by 2.
Epsilon by 2, Win?
What's that? It's going to be absolute plus positive or negative epsilon over 2.
Evan? Julia?
Epsilon.
Epsilon over 2, I assume that that you guys with your hands up, and I'll try to remember who you are. Everybody is right. Epsilon over 2 will do, right? Right? Everybody, epsilon over 2, if I want, here's my L, if I want to stay within epsilon, and epsilon can be any number, all I need to do is to stay within epsilon over 2 down here, and then the function won't go more than epsilon away. Okay? And you probably see that intuitively, right? You probably noticed the pattern, right? There's a pattern here, right? If I wanted to stay within 1, the radius here was what? If I wanted to stay within 2, the radius was 1. 1, it was a half. It was always a half, right? What we call the delta here was always half of the epsilon. Okay, and you see that no matter what epsilon you choose, you can answer the question, right? So here's the thing. If the limit is really L, right? The limit of f of x is L as x approaches c. Then for any epsilon, one can answer the question, how close must x be to c to ensure f of x is within epsilon of L. Okay. So you can do it for any epsilon, and this turns out to be how you define the limit. This is how you define the limit. The ability to do this is how we're going to define the limit being is what we're going to take as the definition of the limit being L. So I'll say it again. If the limit really is L, then no matter what epsilon you're given, you can answer this question. Right? You can find a place. Right? If the limit really is L, then if somebody says, I want you to stay between here and here, you can answer it. Right? If somebody says, I want you to stay within this tolerance of L, maybe there's a place where that tolerance is satisfied. Right? If no matter what tolerance you're given, there's a place where that tolerance is satisfied. Okay. No matter what tolerance is given, there's a place where that tolerance is satisfied. Okay. This turns out to be the crucial idea or the crucial property of limits, that you can satisfy any tolerance. Let me do a little bit of algebra here that will make things a bit clearer, I hope. Okay. So the question was, what x minus 3 less than delta would ensure 2x minus 6 was less than 0.1? Right? Like, how close did x have to be to 3 to ensure that 2x minus 6 was less than 1? Okay. Right, so I'm saying what we were doing before, and I'm gonna do it in an algebraic way so that you don't have to guess about it. Okay? So here's how you would do it just purely algebraically. You'd say, well, right, you're trying to figure this out. How close does this have to be? how close must x be to x be to 3 to ensure this guy is close to is within 0.1 of 6? Okay. You say, well, I want this thing to be small, to be smaller than 0.1, right? I want this thing to be smaller than 0.1, and you notice, observe, this thing on the left is the same thing as twice the absolute value of x minus 3, right? Right? The absolute value of 2x minus 6 is the same thing as twice the absolute value of x minus 3, right? So, if x minus 3 is less than 0.05, we see that 2x minus 6 is less than 0.1. Right? So that gives this to us, right? So our delta, right? So delta 0.5 will do. Right? I'll write it again, right? For if x minus 3 is less than 0.05, then twice absolute value of x minus 3 is less than 0.1. But that means 2x minus 6 is less than, absolute value is less than 0.1. Right? So whenever these guys are within 0.5 of 0.05 of each other, these guys will be within 0.1 of each other. Give me 1 second to now suppose we're asking for what condition x minus 3 is less than delta are we guaranteed that 2x minus 6 is less than epsilon? Well, you do the same thing, right? Delta being epsilon over 2 will do, right? For if this thing is less than epsilon over 2, then this thing is less than epsilon. Right? So as long as x is within epsilon over 2 of 0.3, of 3, then the function is within epsilon of 6. Okay. So you can see it, you can see it algebraically. And that's what we've done during the homework. Okay, that's it for today.